This graph shows the ultraviolet absorption spectrum of vitamin A. We are looking at a smoothly ascending and descending curve, spanning hundreds of nanometers, peaking precisely at 324 nanometers. To plot a curve like this, an instrument must measure how well a sample transmits light across a wide, continuous range of wavelengths. The math relies on a simple ratio: the radiant power of the light striking the sample compared to the radiant power that manages to pass through it to reach the detector. For that ratio to yield accurate concentration data, the incident light hitting the sample must be absolute and unwavering. This requirement defines a continuum source. It is a radiation source where the radiant power output remains highly stable and does not drop sharply over a wide range of wavelengths. Without this unbroken baseline of incident light, calculating precise molecular absorption across a full spectrum is physically impossible. The mathematics of transmittance demand a flawless supply of photons. A modern analytical laboratory requires a spectrophotometer to scan continuously from the deep ultraviolet at 190 nanometers all the way through the near-infrared at 800 nanometers. Designing an instrument to achieve this reveals a significant engineering challenge. No single light generation mechanism easily spans the high energy demands of the ultraviolet region and the lower energy requirements of the visible spectrum. Generating visible light is calorically simple. We have used heated filaments to produce visible photons for over a century. The ultraviolet range requires significantly more force. A visible photon requires relatively low kinetic energy to produce. An ultraviolet photon requires a massive energy density to breach the threshold of the UV spectrum. To execute a full spectrum scan, engineers must stitch together entirely distinct physical generation mechanisms. Inside a single machine, they must force intense, isolated bands of electromagnetic radiation into a controlled optical path. To understand how a modern spectrophotometer functions, we have to look at the physics governing its primary light engines. We begin with the region spanning from 350 to 2500 nanometers, covering the visible and near-infrared bands. The standard, robust source for this specific spectral block is the tungsten filament incandescent lamp. This lamp relies on joule heating. When electrical current meets resistance in the thin wire, that resistance manifests as intense heat. The current forces the tungsten wire to reach white heat, stabilizing at a temperature of approximately 3000 Kelvin. At this extreme temperature, the glowing filament acts as a classic Blackbody radiator, emitting a continuous spectrum of light based entirely on its thermal state. Plotting this thermal emission curve shows its peak intensity across the visible and near-infrared wavelengths. But it has a hard physical limit. Photon output is tied strictly to temperature, so energy distribution drops at shorter wavelengths. Approaching 350 nanometers, radiation intensity sharply crashes. Thermal black-body radiation lacks the raw energy density required for deep ultraviolet analysis. A heated wire cannot generate enough high-energy photons to produce a UV signal. Analyzing the rigorous ultraviolet region, from 160 down to 400 nanometers, requires a different approach entirely. Thermal emission is abandoned here. Instead, the instrument relies on electrical excitation. The primary engine for UV spectrophotometry is the low-pressure deuterium discharge lamp. This introduces a fundamental engineering question. Exciting a discrete, specific gas molecule normally produces a sharp line spectrum of specific colors. We need a broad, continuous, unbroken band of ultraviolet light. The solution lies in the specific kinetic equation governing deuterium dissociation. First, electrical energy is pumped into the gas, exciting the discrete diatomic deuterium molecule. This places the molecule into a highly unstable quantized energy state. It cannot hold this extra energy for long. Almost instantly, the unstable molecule violently dissociates, splitting into two separate atomic species. The physical act of splitting forces the molecule to shed its excess energy by emitting a single ultraviolet photon. The outcome depends on how the initial, fixed amount of electrical energy pumped into the molecule is partitioned across the resulting pieces. The total energy is split between the newly created photon and the kinetic energy of the two departing atoms. Because the kinetic energy of those departing atoms can vary continuously from 0 to a maximum limit, the remaining energy left over for the photon must also vary continuously.
Deuterium lamps achieve a true UV continuum by converting a fixed electrical input into a sliding scale of kinetic and photonic energy, generating every wavelength needed for the ultraviolet scan. Standard hydrogen gas can also perform this dissociation process, but instrument manufacturers specifically use the heavier deuterium isotope. Deuterium has a larger atomic mass. When the electrical discharge occurs, this mass constricts the arc into a much tighter, narrower path. This spatial constriction produces an intense ball of radiation, yielding 3 to 5 times greater photon intensity at the extreme short wavelength end of the UV range. For environments demanding even more intense continuum radiation across both the UV and visible bands simultaneously, instruments use a xenon discharge lamp. This requires an extreme internal environment. Xenon gas is trapped inside the lamp under 10 to 30 atmospheres of pressure. By applying low voltages across a rigid 8 mm gap between two tungsten electrodes, an intensely bright electrical arc forms, providing greater UV output than a deuterium bulb. Not all lamps are designed to produce a continuum. The low-pressure mercury arc lamp serves a completely different function. Electrical excitation of mercury vapor does not dissociate the molecule. It simply excites the electrons, which drop back down in strict discrete steps, generating a line spectrum. This plots as precise isolated emission spikes at exactly 366, 405, 436, and 546 nanometers. Because the space between these lines contains 0 radiant power, mercury lamps cannot be used to scan an unknown sample for broad absorption bands. Instead, these sharp lines provide exact known wavelengths. They are utilized to calibrate the wavelength selectors of the instrument itself, or to serve as static detectors in liquid chromatography. Lamp selection dictates a rigid physical trade-off between broad spectral continuity and targeted raw intensity. Let's return to the primary objective, achieving a seamless, uninterrupted scan from 190 to 800 nanometers. Tungsten thermal emission fails below 350 nanometers. Deuterium quantum emission drops off significantly as it enters the visible spectrum. To guarantee full range accuracy, a standard spectrophotometer must physically house both lamps. Looking at the internal block diagram of a double beam instrument reveals how this dual physics is managed. Inside the source compartment, the light paths from both lamps are aligned toward the monochromator. During a live sweeping scan from the UV up into the visible range, the instrument employs an automated mechanical toggle. At precisely 350 nanometers, the optical path physically switches, dropping the deuterium lamp out of the alignment and rotating the tungsten lamp into position. This mechanical handoff ensures the sample receives an optimal, unbroken stream of incident power across the entire spectrum. The instrument seamlessly swaps high-energy quantum physics for extreme heat thermal physics without interrupting the flow of the scan. The spectrophotometric light source is a functional orchestration of thermal physics and quantum mechanics, engineered specifically to illuminate the invisible properties of molecular structures. Let's return to the primary objective, achieving a seamless, uninterrupted scan from 190 to 800 nanometers. Tungsten thermal emission fails below 350 nanometers. Deuterium quantum emission drops off significantly as it enters the visible spectrum. To guarantee full range accuracy, a standard spectrophotometer must physically house both lamps. Looking at the internal block diagram of a double beam instrument reveals how this dual physics is managed. Inside the source compartment, the light paths from both lamps are aligned toward the monochromator. During a live, sweeping scan from the UV up into the visible range, the instrument employs an automated mechanical toggle. At precisely 350 nanometers, the optical path physically switches, dropping the deuterium lamp out of the alignment and rotating the tungsten lamp into position. This mechanical handoff ensures the sample receives an optimal, unbroken stream of incident power across the entire spectrum. The instrument seamlessly swaps high-energy quantum physics for extreme heat thermal physics without interrupting the flow of the scan. The spectrophotometric light source is a functional orchestration of thermal physics and quantum mechanics, engineered specifically to illuminate the invisible properties of molecular structures.